This is the fourth lecture of week 3. So in this lecture, we're going to talk about some examples of nonlinear specification. So nonlinear model actually lets us examine more nuanced questions about the relationship between test score and student-teacher ratio. For example, instead of simply asking what is the effect of student-teacher ratio on test score, we can ask more nuanced questions such as 1. Are there nonlinear interactions between percentage of English learners in the school district and student-teacher ratio? In other words, are small classes more effective when there are more English learners? Or another question that we can ask is, are there nonlinear effects of class size reduction on test score? In other words, does reducing a class size from 35 to 30 have a different effect than reducing a class size from 20 to 15? So in this lecture, we're going to test these hypotheses using the data that we have and try to answer these questions. So let's first look at the linear regression model. Here in this table, we're showing 7 different linear regression models, and each column represents unique regression models. So let's look at model 1 and model 2. In model 1, we're regressing test score on student-teacher ratio, percent English learners, and percentage of students who are eligible for subsidized lunch. The difference between model 1 and 2 is that model 2 includes the average school district income. Also note that these coefficients have stars, and 2 star means that it's statistically significant at 1%, and 1 star means that it's statistically significant at 5%. So it helps you quickly see which variables are statistically significant without having to look at p-value or calculate t-statistics using the standard error. So just comparing the two linear regression model 1 and 2, we can see that the model 2, which includes the school district income, the coefficient for school district income is significant. Second of all, for model 2, the main coefficient of interest, which is STR in this case, actually declines from model 1 to 2. And this decline is pretty significant, which means that model 1 likely suffers from omitted variable bias. So our preference would be to include the school district income in the model. So the first question was asking whether the effect of student-teacher ratio on test score varies by the percentage of English learner in school district. In order to answer this question, what we can do is compare the model that doesn't include the interaction term of student-teacher ratio and percentage English learner, and compare this to the model that includes the interaction term. So let's look at the model 3 and model 4, where we're regressing the test score on student-teacher ratio, the binary variable of whether the school district has a high percentage of English learners, and the interaction between this binary variable and student-teacher ratio. The difference between model 3 and 4 are the fact that model 4 includes these 2 additional control variables. As you can see, model 4 coefficients are generally smaller than model 3, but none of the coefficients are actually statistically significant, especially looking at the interaction term of binary variable of high percentage English learner and student-teacher ratio. We can see that it's not statistically significant at 5%, which makes us believe that perhaps there is no interaction between the percentage of English learner and student-teacher ratio. In other words, this regression model indicates that The effect of student-teacher ratio on test score doesn't seem to vary by the percentage of English learner in a school district. Next, we're going to move on to the second question of looking at if the effect of STR on test score varies by STR value. And we're going to look at the nonlinear function of STR and see if any of the coefficients of nonlinear function are significant. Looking at the regression 5, which regresses the test score on student-teacher ratio and quadratic term of STR and cubic term of STR, the model also includes the binary variable of whether the district has a high English learner and the two control variable that controls for the school's economic characteristics. In this model, you can see that the coefficient for quadratic term of student-teacher ratio and cubic term of student-teacher ratios are both statistically significant at 1%. So this makes us believe that the linear model is probably not the best fit on the data, and that either the cubic or the quadratic model probably fits the data better. We can also conduct an F-test that has a null hypothesis of quadratic term and the cubic term both being equal to 0. Looking at the test statistics and a p-value, we can see that the p-value is actually less than 1% and 5%, which means that we reject the null at both 1% and 5%, which means that at least one of these terms, either the quadratic or cubic, is not equal to 0. And this reaffirms our previous conclusion that linear model is not the best fit. Last thing that we want to look is Model 5 and Model 7. Model 5 and Model 7 both include the quadratic and cubic term of STR. The only difference is that Model 5 includes the binary variable of the percentage of English learner being high, whereas the Model 7 includes the actual continuous variable of percentage of English learner. So as you can see, the main coefficient of our interest doesn't really change that much, whether we include this percentage English learner as a binary variable or a continuous variable. So it shows that it doesn't really matter how we include this percentage English learner variable in the model. So last thing we can do is look at these graphs visually. So here we're plotting both the linear regression line as well as the cubic regression line from Model 5 and Model 7. Just looking at the graph visually, it seems like the cubic regression line fits the data better, but it's hard to tell because most of the lines are overlapping. So we have some strong evidence that the model should not be linear, and it's probably likely to be cubic, but we also want to check if this nonlinear function actually varies by percentage English learner. So in order to do that, we're going to include the binary continuous interaction terms that multiplies the binary variable of having a high percentage of English learner in school district with student-teacher ratio and student-teacher ratio quadratic term and the cubic term. So Model 6 includes these 3 additional interactions in addition to our quadratic and cubic terms. And as you can see, the coefficients for the interaction terms are all statistically significant at 5%, which seems to indicate that this nonlinear effect of student-teacher ratio and test score seems to actually vary by the percentage of English learners in school district. We can also conduct an F-test with the null hypothesis that says that all of the interactions term that we included is equal to 0. The F statistics and the p-value of 0.046 is less than 0.05, which says that we reject the null hypothesis and conclude that at least one of these interaction terms is not equal to 0. So this seems to indicate that the nonlinear relationship or nonlinear effect of student-teacher ratio seems to vary by high percentage, whether the district has a high percentage of English learner or not. Let's look at these regression functions visually. So here we're plotting the previous regression function for cases when the high percentage English learner binary variable is equal to 0 and when this is equal to 1. As you can see that in almost all cases, when the school district doesn't have a high percentage of English learner, it seems like the effect of student-teacher ratio is greater on test score than when the school district actually does have a high percentage of English learner. Another interesting thing to note is that if you look at data points where between student-teacher ratio is around 17 to 23, the line for high EL0 and high EL1 is more or less parallel. So they actually have similar slope. So what this means is that even though in general, schools with lower percentage of English learner has higher test score, when the class size actually changes by a certain amount, the effect on test score is the same regardless of whether the school district has a high percentage of English learner or low percentage of English learner. So this indicates that the effect of student-teacher ratio on test score doesn't really vary by the percentage of English learner. And the reason why we were getting the result that they actually vary was because of the area where we don't have a lot of observations. So when you look at observations where the student-teacher ratio is less than 17 or greater than 23, there are not that many data points there, but this is why, because of this area, we are getting the result that the nonlinear student-to-teacher ratio effect actually varies by the percentage of English learner. So to answer the question, the first question that are there nonlinear interactions between percentage of English learner and STR? The answer is there is at most very weak evidence that the effect of STR depends on percentage of English learners. For the second question of if there is a nonlinear effect of class size reduction on test score, we do find strong evidence that the effect of student-teacher ratio is greater for moderately sized classes than very small or very large classes. So to summarize, we have looked at many different functional forms of nonlinear regression, and using functions of independent variables such as log of x or the interaction term x1 times x2 allows us to use estimation strategy or inference from the linear multiple regression model. Also, interpreting the coefficient is model specific, but one of the general rules is to see what happens to y when x changes by small amount. Lastly, there are many different nonlinear specifications that are available, and sometimes choosing which nonlinear model to use is a very subjective thing. So you have to rely sometimes on your expert knowledge or economic theory to decide which out of the many nonlinear functions that best fits the data.